iC-House Integrated Circuits.
I'm Joachim Quasthoff and responsible for sales and applications engineering of encoder-related devices, including optical sensors and interpolation ICs. Well, there are many ways to sense a position or an angle, and that's the topic of today. I will be assisted later on by Silvan for the hands-on demonstration. Now, what I'm going to talk about, it's mainly solely on optical absolute encoder ICs and on topics what we as application engineers, or I should say you also, need to know about scanning technologies. I will take you back a while and then forth to the latest development we introduced, namely the PNE series. In the second part, we will give you a live demonstration executed by Silvan, and finally we do have time for your questions. Well, let me take you back 3 decades. Initially, we did a bipolar design, namely the iC-WG scanning a 13-bit gray code. So this was a complete differential scanning focusing on bipolar technology. And at this time, we were able to higher the resolution of those standard industrial encoders to 14 bits. Well, you may note the radial scan length of 9 mm is kind of bulky, so this requires a powerful LED and also a larger lens. Well, anyway, it fits, at this time, it fits into the standard industrial encoder of size 58 mm, as illustrated here. A while later, when CMOS came into play, we have been able to reduce the radial scan length to 7 mm, involving interpolation to higher the resolution without the drawback of adding more bits which we need to scan parallel. So this system on-chip design, again, differentially scans the information, plus in addition, there's a leading and trailing sensor to provide a glitch-free code reading. You see this complexity here, about 100K transistor functions, so this allows us to include also interfaces, for instance, the speedy BIS interface you won't miss today anymore. Our first introduction of non-US-based systems was around 2008, and to see clearly the advantages, we reduced the radial scan length to just 3 mm. And also we decided to split the sensor from the evaluation circuit to be able to optimize both components independently according to the demands. In this system, there are 3 tracks providing incremental information, but the absolute information is more or less in the phase shift between, so that is why I still would call it a kind of tangential code. Later on, the iC-HausVideo system showed up. This is a system utilizing pseudo-random codes, and it focuses on safety applications. Actually, it's meanwhile a SEAL-certified compliant item, and you can use it standalone, providing 15 bits plus a safety word, or if you go for high resolutions, you can connect up an interpolation device to obtain up to 24 bits. Finally, we are presenting the iC-PNE series, and you see here we get back a little bit in history, so we turn it, we do gray code again, plus the non-US on top. And why that is, I'm going to explain this. And in the back end, we have a modern high-end interpolation engine providing a much higher resolution. You may note that here 180 nanometers is in gray. Well, that makes up another story, but that's more what I can cover today. A little bit back to the constructions. What kind of arrangements we do have? Well, first of all, on the left-hand side, we see a transmissive arrangement where an LED provides a collimated beam which shines through the code disk through a reticle onto the detector. In the center, we have more or less the same system. Again, the LED illuminates the code disk, but here the reticle is replaced by a clear glass lid, and the structure is directly on the detector. And on the right-hand side, we also introduced reflective ICs, and you clearly see the advantage. It runs at a much higher reading distance here. Just an introduction. Now the question is, what are the pros and cons of all those concepts? Now, first of all, here on the left, the reticle would allow us to customize the scale to any diameter you are asking for. Also, the line count can be modified with less efforts. So there's a high flexibility. On the other hand, we have seen that the distortion you are getting on the sine-cosine signals are not the optimal values we like to have, especially not when we are heading for extreme resolutions. Not so in the center here. This phased arrays, meanwhile, allows us to generate a really low, crystal clear sine-cosine signal, allowing precise interpolation. So that is a benefit, while certainly at the expenses of flexibility, since now we need to have a special phased array design for each diameter you are asking for. And that's why we developed a portfolio of ICs, what I'm going to explain you. On the right, what I need to mention is our reflective type of ICs, they run at about 4 times raw native line pitch, but makes it a little bit harder to obtain the highest resolution or obtain the accuracy. I'm not saying it does not work, but it's a little bit harder. Well, the advantages of this design are in the operating distance and also in the placement tolerances for the ICs. Well, regarding the mechanical arrangement, well, you have mainly two choices how to build the encoder. You could place the LED on side of the flange, and in this case, the main PCB here carries the detector, and it must be installed a coplanar to the code wheel. Or it may be subject to vibration, and generally it will be subject to thermal expansion. So this is a mechanical thing, what needs to be solved. Those circumstances are not even better if you turn the system, if you place a scanner down there, while you are not getting rid of all those issues. It changes the world a little bit. My question from this was, is there any scanning technology which is best usable for those circumstances? I did a small table on this. We have the WG gray code scanner on the left, then the binary reader, the LGC system, the pseudo-random code system, RZ here, and then the early nonlinear system introduced around 2008, reading 256 lines, and on the right-hand side we have the new PNE. That is the device we are going to demonstrate later. Actually, what is the difference? Are they large? No, they are not, as long as the aperture, the slot size of the disk is the same. We can see that the early nonlinear systems here, they can live with a really raw disk, so this increases the air gap. That is quite nice to have, but it does not deliver the resolution we are asking for. What was also quite good is the tolerance for the calculation of the nonlinear, so this can be done very easily. Now with the final PNE, we managed to obtain the same tolerances here together with an output of 2048 CPR, what is desired for many industrial applications. I will go back into details on the next slide. Now, how is the system working? Well, our code will supply here 3 tracks with incremental lines. They are different to each other. And all those sine-cosine signals are converted, they are digitized by a precision sine to cosine assigned to a digital converter, and then afterwards there's some computation to determine the absolute position. Well, there's some math. I don't like to go into this detail, but the only point I'd like to mention is that it is mainly the master track which is relevant for its accuracy. You see it here. We get our LSBs in the position word only from the master track. Everything on top just says where we are. Well, now with the PNE, we are reducing the number of lines to 256. So this makes the non-use more robust for the calculation. But of course, how do we manage to get 2048 CPR? We scan just a sector. We shrink this into 45 degrees. So this adds a question to how to initialize where we are. And that is why we added this gray code. Actually, we read a 4-bit gray code. It resolves just 22 degrees, but that's fine enough to initialize our engine in the absolute position. What are now the benefits? Why do we analog? It sounds a little crucial, but actually it's not. Since any modern detector or any modern encoder circuit will use sine-cosine signals to interpolate or to obtain a much finer resolution. So we do the same here, just we add 2 more tracks for the absolute information. And this is the main point. We do it smaller. Having just 3 tracks, the whole device built smaller. That is a key advantage here. And so we save LED power. Now you can use just a 5mm LED illuminating this 3-point-something in diameter. That saves power. Finally, assuming or imagine you would be satisfied with a 20-bit resolution already, then you can run with the very raw scale as shown on here. That's 26mm, 256 lines. So this would increase the air gap due to the larger aperture. That is quite nice and easy to install. So, having 2 components, you see on the right picture here, the sensor and the evaluation circuit, it's very cost-effective in small board space. Now with the PNE, so we get extremely low distortion, a crystal clear reading of the sine and cosine, we will show it later on. The reliability is improved due to the higher phase margin for the calculation. And what we also implemented is the gray code detection runs with very low power. It starts from 1.8 volt. So this would allow you to use it for non-volatile revolution counting. It would need an evaluation circuit plus a battery suddenly, but it is already included here, this non-volatile sensing, this low-power sensing, sorry. So what are the drawbacks? Well, you have to calibrate the system, but I will show you how easy that is. Before I do that, let me introduce you to our sensor portfolio. There are many components. We did some for 18 millimeters in diameter, 26, 33, 39. So we cover the whole range required. And in terms of CPR counts, we start with 64. And with the new items, we are running 8 times 64 or 8 times 256. So here you see this non-use repeats over 45 degrees. And the advantage here is clear. We can install it at the same single phase error tolerances or limits, which we know already from earlier systems. And those have been improved for years in the field. Now, let me introduce you the iC-MNF encoder processor. So you may have noted we get 3 channels incremental signals, sine, cosine of differential signals. So we need to have a precision analog front end with signal conditioning, and this allows you to implement some error correction on the analog signals. This can be done on command. So this MNF Stone, it already owns some state machines to do this. On command, the self-calibration performs up to an accuracy of 0.1% related to the signal, to the analog signal. That's more than what you need. The conversion, it's simultaneously sampling all inputs and subsequently as a conversion with up to 14-bit in resolution. It's very fast, so the settling is within 3 microseconds, so this is really an extremely fast conversion, allowing you also to update very quickly. The engine includes a non-use calculation according to the different scales you are using. So it's a complete single-turn and multi-turn data processing. And the multi-turn interface is quite flexible. You can scale it for any lengths you are connecting here. What is most saving your board space are the included transceivers. So there's an RC422 transceivers for BIS output or SSI, and also so for sine cosine, providing a 1 volt peak differential signal, what you can terminate at the control with 100 ohm. And those world pins here are reverse polarity safe. So that means, so if your customer accidentally would connect 5 volt supply to an output, it wouldn't damage the device. That is quite helpful. There's an SPI interface if you stay embedded, so this eases the connection of an MCU. For instance, if you would need to convert the outgoing data to a different protocol. And the engine runs at 5 volt over the full temperature range, and the power consumption is quite reasonable for the coverage here. So what I did not yet mention, the chip also takes care of this battery switching in case you would add this battery-powered multi-turn. So you see, sorry, my pointer is missing me. So you see there are just 2 components which make up the system, and there's not much externally, so the whole system builds very small. The next slide is introducing you the system sketch, how we built the system to do the singleton. So we have the LED here, a blue LED illuminating the disk, and the scanner is providing sine cosine signals which are connected to the MNF encoder processor. And besides, the 4-bit gray code is scanned by the MCU, converted to SSI for easy processing on the MNF chip. So that is a complete sketch for the singleton function. And if you would switch to a non-volatile memory, you would benefit from the battery switching of this C. The battery now powers the MCU, and everything is controlled on here, powering up the PNE, flashing the LED, getting the reading, tracking the revolution, and storing it with help of the battery power. Now the complete, someone is standing in between, I'm sorry. The complete sketch, complete hardware you're going to see is we have the device under test here in the center. We connected an ampere meter to monitor the battery consumption here. So this single turn initially passes on sine cosine, so we can demonstrate it here on a synthesizer engine that's actually a kind of software-based oscilloscope, what allows us a very fast Fourier transformation, calculation of the total harmonic distortion, and the inspection of the sine cosine signals for nonlinearity things. The device here is connected with an access to our drive. This drive includes a reference encoder to see that the multi-turn is captured here, and we are using now the capability of the BIS interface to chain it up over a BIS adapter up to the PC, where we have a GUI to do the operations here. Well, now it's time for practice, and I welcome Silvan to take it over.
Thank you so much, Joachim. So, warm welcome from my end. My name is Silvan Ettler. I'm Sales and Applications Engineer for Encoder Products at iC-Haus, and I'm very happy to guide you through this live demonstration of the hardware that Joachim just introduced. So, taking a quick step to the right and giving an introduction on the hardware we have available here. So the blue box here is one of our demo drives, and it includes one optical reference encoder inside I will use later on. And on the shaft of the motor we have a 33mm code disk installed with 2048 PPR, so lines. And on top of it, you can see this tinier PCB here that includes the blue LED, our ICTL46, that illuminates the code disk. And the optical projection is then received by the iC-PNE 3348 that is sitting on the sensor PCB here. And quite close to the sensor front end, there is the iC-MNF 3-channel Nonius interpolator that receives the master, Nonius, and segment analog tracks as introduced by Joachim. And the gray code we use for the sector detection, the 4-bit gray code, is sent to a low-cost, low-power microcontroller that is sitting also on this PCB that does the conversion from the parallel gray code into an SSI data word to be fed into the iC-MNF to initialize the system with an absolute position. So first things first, what I like to show at the beginning is you can currently see the motor is in standstill, and I'd like to highlight the resolution of this encoder system. So I'm very carefully turning the shaft to the maximum position. So I try to hit almost 360, okay, that comes close enough. So as you can see here on the left side of the screen, there's a single turn position dial. You can see the angle value here, and below it, there is the decimal value of it, and it's 33 million something angle steps over 360 degrees, which is equivalent to 2 with the power of 25, so 25 bits of resolution. And aside from the very high resolution the system provides, you can see if I'm not touching the mechanics, that there's hardly any flickering going on in the LSBs here. So this is quite outstanding, a very accurate system as well. So not only high resolving, but also precise. And this is what I like to show on this other screen here. So I'm taking one step back, and I'm happy to introduce the synthesizer 2 encoder measurement system that is kind of a combination of a high-end oscilloscope and software-based evaluation tool built for encoder-specific measurement tasks. And before I'm going to show you something here, it makes sense to share the screen so you are able to see what I'm doing here. So please give me a second. All right, so we have connected the master track of the iC-PNE, respectively the iC-MNF system, to the synthesizer input. As Joachim already explained, the master track is the one that is responsible for achieving the high resolution and also the high precision in the LSBs. So currently we are in standstill, and I'm acquiring data here. And when I turn on the drive now, you will see the sine cosine signals on this scope view. I'm doing so. All right, there we are. Here are our sine and cosine signals of the master track. And for doing encoder analysis, signal analysis, we at iC-Haus love to use this encoder adjuster tab. and I'm going to highlight some of the key figures that we have here. So let me say this system is signal adjusted by the iC-MNF and also uses the auto calibration, the functions of the iC-MNF. So we have a calibrated encoder system here already. And what you can see on this screen is an analysis of the amplitude of sine and cosine and their difference. Below there is the offset analyzed, and the last one with those green bars is the phase of sine to cosine. And I'm not going too much into the values here, but as a summary, what you can see here, the bars are bright green, the signal quality is excellent. And this is proven by this blue bar, which is the maximum interpolation accuracy. Let me give an explanation here. So this number gives an idea of the accuracy that can be achieved of one sine-cosine period. One sine-cosine period of the 2048 base information we have available on the code disk. And we end up with an interpolation accuracy of more than 10 bits with this system, which is an outstanding value. Aside from those key figures, we have a last one I want to go into detail, which is the frequency domain, which is also very important when it comes to building high-resolving, high-accurate encoder, optical encoder systems especially. And there you can see the values for the total harmonic distortion of the sine and cosine, so the THD. And we have a fast Fourier transformation, an FFT analysis module for the synthesizer too. And I want to show you the spectral analysis in real time by clicking on the spectral analysis tab. So you can see the live spectrum of our rotating system now, and our base frequency, our main frequency is at 5 kilohertz currently. And when I look at the second order frequency here, roughly at 10 kilohertz, you can see that it's below minus 60 dB. So that corresponds somewhat to below 0.1% total harmonic distortion, which is a very good value for this analog front end. And this is the reason why we do have not only this high resolution, but also a very accurate encoder system with this chip combination. So that's it for the single-turn portion, single-turn part. I now want to step over and give you another feature, point out another feature, which is a multi-turn function that you can get basically for free with those chip components by utilizing a battery. But before I'm switching off the, okay, that's fine. All right, so stepping back to the right here, the right side that you can see here on the screen, it shows the multi-turn values, in particular 2 multi-turn values. One on top that is coming from the reference encoder that is sitting inside the drive here. And the below one will then come from the iC-PNE MNF microcontroller system and will be backed up by a battery. And to show you the power consumption of the multi-turn in motion, we have installed a live battery current measurement here below. So let me give a quick introduction what will happen. So if I hit this button, the whole encoder will be disconnected, will be powered off, and will automatically switch into a low power battery mode. And then the microcontroller, for a very short glimpse of time, flashes the blue LED and turns on the iC-PNE 3348 digital front end for the gray code. That short glimpse of time is sufficient to scan the gray code, then save it non-volatile and being available again when powering on the encoder system so that no counts will get lost in power off state. So by doing so, you will see I won't be able to communicate via BIS with the encoder anymore, so no values are going to be displayed here. And when I'm going back into power on mode, you will see that there's a jump in the multi-turn values. So I'm switching off the encoder now. The encoder is disconnected, and you can see we are still in motion. You can see there is some battery current drawn here, roughly 10 microamps for this speed here. And when I'm going to switch back on, you will see that the whole system, the encoder system, will be initialized with the multi-turn value that is still being counted here. So we expect a jump here in the multi-turn values when powering on again. I'm doing so. So see, we had a jump of roughly 90 counts, so no counts were lost in power off state, and that concludes that you can build a very efficient multi-turn system with just utilizing a battery on top of this single-turn system here. So that's it for my demonstration. Of course, there's a lot more to explore. We are very happy to receive and answer your questions, and I'm finally passing the ball again to Joachim for a quick summary, and I say thank you for your attention.
Okay, so let me do the summary of the serial absolute bis encoder, what Sylvan demonstrated us. So we get an extreme resolution, 25 bit per revolution per 360 degrees. There's an outstanding accuracy, about 0.6 arc seconds. So this is an electronic accuracy which is much higher than your target accuracy does do. But I'm just pointing it out. This is something around 21 bits. Where does it come from? Okay, we have 11 on the disk, and we calibrate the analog signals with 10-bit accuracy, so that's where this number comes from. Then we can do this GUI-supported self-calibration for easy commissioning, and I can point out it can be sufficient to calibrate only the master track and keep the other both tracks as they are with a default setup. Since the iC-PNE is a very nice sensor to do this. So we have a portfolio of different disk diameters. So this allows you to build small devices or larger devices, and beyond that, well, we stop at the diameter 60 millimeters or so. If you go beyond that, potentially this strategy or this gray code scanning with non-volatile revolution tracking, this can also be used to blow it up to very large diameters. Well, this setup here allows you to go with servo speeds up to 6,000 RPM, several hundred kilohertz, 200 kilohertz in sine frequencies, and to benefit from the sine cosine output with 2048 CPR, which is delivering directly off the stone this 1 volt peak-peak differential signal, powerful to be terminated with 100 ohm. The offset can be calibrated down to less than a millivolt, and as just demonstrated, the distortion we expect is below 0.1%. There's headroom for memory, so you can include your user memory or manufacturer memory to include an electronic data sheet, or if you needed, a motor ID plate for the whole drive. 5-volt operation over the full temperature range is featured, and and this reverse polarity protection, including the BIS transceiver with 10 megahertz, is a feature what eases your hardware around it, very small external components. Footprint is very low on the board. This makes a small PCB, saves costs. And as introduced, the battery buffered multi-turn sensing is an option you can go for. So that's it from my side. We can switch to your questions, Henrik, if there are some.
Thank you very much, Joachim. Very impressive. Appreciate your feedback here. Thank you for your questions, and you can still ask questions whilst we go through the ones that we've already received. So I'll start with the first question, Joachim. So which tolerances in the axial and the radial directions are acceptable in this application?
Yes, I can imagine where this question comes from. You see that we have now more tracks on the same opening. Of course, the gray codes are shrinked so that you can now look at the gray code output to see if you are in the radial placement is okay. And if I remember right, it's about plus minus 20 micron to be in the tracks. Tilt angle is not so important. You can calibrate it electronically. Regarding air gap, that's physics. The aperture is small, around 20 micron, I would guess. So this means that if you install a blue LED with good beam quality, then you benefit that you can blow up the number of, I would multiply the aperture. Usually there's a rule of thumb saying 2 times, 3 times the aperture would do perfect. Now here, the blue LED allows us to go for 5 to 6 times the aperture. So finally, you would end up, if you do this encoder as we demonstrated here, you would end up between, let's say, 80 microns to 160 microns in air gap.
Okay, that's impressive. Yeah, thank you. Next question is, the signals are very stable, and they say that's impressive. So how do you drive the code disk here in this application?
Okay, what you saw on the synthesizer is an averaging result over I think 2 revolutions. Of course, our drive is also controlled, so this has not a high speed ripple. So this is a motor control involved to keep the velocity very close at 300 RPM, what then generates approximately 5 kilohertz in sine frequency.
Okay, good. The next one is about the LED. So is it possible to use a red or an infrared LED in this application?
Some of those components allow the infrared LED, but some, especially when we have this 2048 line count, those are optimized for blue light. So you need to keep in mind that the detector design is very close to the surface of the detector, and this shifts the sensitivity towards blue or towards red. Red can still work. So far, we have not seen that red LEDs provide us the dot size we need, but I can imagine it does work. We promote the blue LED so that we can provide the whole kit, including the disk designs, LED sensors. That is proven and fits together.
Excellent, thank you. Okay, next question is, which absolute encoder IC or which scanning technology is most robust against dirt and dust? Is there a quantitatively specification regarding dirt?
So in general, optical sensing is more sensitive as any magnetic stuff. And regarding the optical clarity of the surface, when we ship our components, those have been inspected with a pattern recognition to guarantee that the glass lid is clear. So finally, if you place it into your environment, of course, if you get some contamination on the surface between the sensor and the disk, so this can impact the function. I would not say it would kill the gray code scanning, so this is quite robust. It could impact the sine cosine quality, but we have seen that there is we are much better than we needed, so there's room to get some dirt. Okay. But I cannot rate it how much.
Okay, understood. Thank you. Good answer. All right. Do you have similar products for linear encoders?
Not yet. Actually, all those PNE models are banded to allow small disks. There is no linear version yet.
Okay, thank you. Does the system provide a second position value for functional safety?
No. The MNF is adding a very longer CRC if you need it, but actually there is no second channel providing a a kind of safety position word.
We have the RZ.
You could, yeah, the RZ, I introduced it just shortly, this PLC scanner, the iC-RZ. This chip includes 2 channels on 1 stone. Well, that makes it easy to set up operation. You align one and you've got 2 channels aligned. Here you could just take another sensor in chain with the BIS output. That can work.
Okay. Okay, so the 3 picosecond delay for both the IC and the sensor delay.
You have different choices how to set up the conversion. Usually, the BIS interface introduces a trigger point to capture the position, and that's what we do. We use this to trigger the sample and hold circuit to freeze the input signal for the subsequent conversion. And so the word is there within a few microseconds. And output, if you go 10 megahertz, very fast. So this allows you, if I remember right, refresh rates beyond 100 kilohertz, maybe 200 kilohertz, so very fast. And in the meantime, we can do other calculations to check if this non-use computation was error-free and so on. I'm not sure if I captured the question perfectly, but...
Okay, if we didn't answer the question perfectly, please send us an email and we will continue to elaborate on this point. So now I have the last question. Is PNE and MNF is very attractive. The question to compare is, in what cases should I use the PZ plus battery buffer device system, and in the other case, PNE, MNF, and LED system? So which applications, which solutions should we use the various systems? PZ battery versus PNE, MNF?
Yes, I know that the PZ engine, the reflective chip, is a very nice engine, and it also provides an electronic accuracy going up to 18 bits or so. Here we are at 21, but 5 arc seconds is what you could expect from a reflective system in terms of repeatability or electronic accuracy. The point is, how accurate are the scales? I did not discuss it on here, but usually the scale you are using, if you have an angle encoder, it could be 2 arc seconds accurate, but a classic industrial encoder, a disk provides you maybe 15 arc seconds. Okay. So the scale determines finally how precise you can be. Of course, I mentioned that the reflective approach reads a rawer scale about 4 times, and that's where the differences come from. But of course, the benefits are clear. You run at much higher air gap, and you have more tolerances for positioning. Well, we offer all those systems. It's up to you to take your selection.
I actually got one more, Joachim.
Okay.
I said it was the last before, but the last one is, are the signals from PNE better than PNH under the same resolution and assembly conditions?
Yes, they are. So on the PNE, we have a younger generation of matching amplifier design, and also the photosensor design is some kind of advanced layout. So I'm confident that you get a much lower distortion from the PNE.
Okay, excellent. All right, that concludes the Q&A session. I want to say a huge thank you to Joachim and Silvan for an excellent presentation. And I also just want to highlight that we will be at SPS in Nuremberg, November 14th to 16th, and we will actually show this demonstration that you have seen here will be at the show. And myself, Joachim, and Silvan will also be present, and other applications engineers from iC House. So we very much look forward to visit you. We will be in Hall 4A, booth 146, and we look forward to see you there. So thank you very much for tuning in.
Thanks for listening.
And have a nice day. Thank you.
Bye-bye.
iC House. Integrated circuits.